Para iniciar os trabalhos, chamo o moderador desse bloco, Alejandro Wagner, diretor executivo da Lacero, Associação Latino-Americana de Acero, e ex-diretor da Agência Argentina de Investimentos e Comércio Internacional.
Bom dia. Vou falar em português, se está tudo bom. Acho que vai ser melhor que em espanhol. Bom, aqui temos uma apresentação muito breve. A ideia é escutar os especialistas hoje, mas eu gostaria de trazer alguns dados interessantes do mercado global, antes de entrar no plano de construção especificamente. E também algumas reflexões, já tivemos algumas hoje. Eu gostei do cara de Arcelor, que falou uma pergunta bem básica, mas também que todos estamos fazendo aqui, acho, que é por que não podemos vender mais, ou por que não temos mais penetração da construção em aço. Só 5% no Brasil, a Argentina está perto dos 5, 6%, Chile é o país mais grande nesse sentido, da construção em aço tem 10%. Então, quando você olha, Grã-Bretanha tem 60%, Estados Unidos tem 50%, e a pergunta é por que não podemos chegar lá ou mais perto de lá. Bueno, acho que essa é a pergunta fundamental destes dias, das jornadas, que faz muito sentido fazer. Então, breve panorama, primeiro, como é isto? Espera aí. Allá. Então, 4 pontos, acho que são 10 minutos, depois eu vou apresentar os palestrantes técnicos de luxo que temos hoje. Mas o primeiro, 2 palavrinhas da Lacero. O segundo, como falava, vou comentar um pouco do mercado global de aço, que acho que dá para falar 2 palavrinhas disso, como estamos no mundo, como estão estes anos, a previsão para este ano, do mundo, Latinoamérica e Brasil. E depois, sim, para falar um pouco mais do setor construção, pontualmente com 2 pontos. Então, isto é a Lacero, basicamente, em um slide. A gente representa praticamente o 95%, 90-95% da produção de aço da Latinoamérica, com sócios, membros em toda a região, Brasil, Argentina, Colômbia, México, as 4 principais economias, mas também com sócios de muitos países de Centroamérica para baixo. Não só produtores de aço, mas também temos muitas empresas da cadeia de valor, muitas empresas que estão hoje aqui, como Prime Metals, Tenova, Danieli, muitos Vale, grandes empresas fornecedoras da indústria, que também formam parte da Lacero. A gente fala de uma média de 65 milhões de toneladas de produção em toda Latinoamérica. E isto também é a Lacero. Eu gosto também de falar disso. O outro é mais uma apresentação como um crachá, ¿no? Mas isto é o que a Lacero é para mim. A Lacero hoje está sendo transformada em uma espécie de think tank, onde justamente, igual como estamos fazendo esta semana com a ABM, a gente está fazendo muitos projetos, coloca ideias na mesa, mas depois se transforma essas ideias em projetos, porque, ao fim e ao cabo, a gente não só tem que fazer relacionamento, mas também tem que produzir produtos que tengan sentido para todos nossos membros. Então, considerando que todos nossos membros, todos os produtores de aço e a cadeia de valor têm muitas problemáticas muito similares, então a gente pensa que com estes projetos pode tentar resolver muitas dessas problemáticas no futuro. Então, acho é a ideia fundamental. Não vou entrar em detalhe, vou compartilhar com vocês, mas aqui você tem, obviamente, os 4 grandes temas: o meio ambiente, economia, educação e uso de aço. Aí, dentro da educação, falamos da palavra educação porque engloba interna ou externamente quando queremos difundir o uso de aço. Gran parte da difusão do uso de aço é educar internamente dentro de nossas empresas, mas também para fora. Hoje falava também na apresentação do primeiro painel, muitos dos problemas de por que não vendemos mais aço para a construção metálica, e muito disso falamos hoje também da educação. Então, um eixo muito importante para nós, e obviamente também saúde e segurança, que é uma iniciativa uma problemática muito importante para a nossa indústria também. Agora sim, um pouco do mercado de aço. Slide nomás para compartir com vocês alguns dados. Em 2020, plena pandemia, a gente já conhece a curva em V famosa, mas falando dos números pontualmente, Latinoamérica caiu perto de 10%, 9, algo por cento, em seu consumo aparente de aço em 2020, mas a subida último trimestre do 2020 e todo o ano 2021 foi de 27%, ano contra ano. Então, queda 10% da Latinoamérica, suba de 26%. 2021, a gente subiu muito mais que todas as regiões do mundo. Então, a recuperação foi definitivamente muito forte e muito mais forte que em qualquer outra região do mundo. E para 2022, a gente está previsionando, a gente na Acero participa em um comitê econômico dentro do World Steel e a gente faz junto à ASO Brasil e a todas as secretarias regionais, faz um pronóstico de consumo de aço para 2022 e 2023. A gente hoje está falando para Latinoamérica uma leve queda de 2,1% para o consumo de aço aparente 2022. Mas, se a gente olha o primeiro dado real, de consumo real, não provisão, real, do primeiro trimestre, a gente está vendo já 4,5% de queda de consumo de aço. Obviamente, vamos a ver mais para frente, o impacto da construção é muito importante aqui nestes patamares. China, 0% para este ano. Eso que, obviamente, vocês lembram, seguramente a China produce e mais ou menos consume também a metade do aço do mundo. Então, obviamente, o patamar de 0% de crescimento faz que o mundo vai crescer mais ou menos também perto do zero em 2022. Brasil, aí você tem o SUMI do Brasil, que queria trazer também. Dentro de 2,1% de LATAM, Brasil representa 25% desse número. E a gente está vendo para o Brasil 8,5% de queda, mas de volta. Se a gente olha o primeiro trimestre, já estamos perto de 16% de queda no consumo. Pode ser que trimestre contra trimestre seja o pior trimestre, mas vamos ver o que vai acontecer para o final de ano. E no termos de produção, que também é importante, outro dado interessante, o mundo está caindo no primeiro quarto de 2022, quase 6%, 5,9% exactamente, traccionado pela China, outra vez, 9% de produção de queda, trimestre contra trimestre, e Latinoamérica, praticamente em produção, estamos mantendo o mesmo patamar por enquanto o primeiro trimestre. Agora, se me ajuda. Construção. Eu falei uma média de 65 milhões de toneladas de produção, mas se falamos de consumo de aço, esto es consumo de laminados de aço. Un dado. Ahí encima, en azul, você consigue ver, estamos falando, 2021, eu falei una suba de 27% de consumo de aço. Eso representó casi 75 millones de toneladas de consumo. Consumo, lembrando, producción local, todos los países de Latinoamérica, más importaciones, menos exportaciones. 75 millones de toneladas. A queda de 2,1 que estamos estimando para este año va a dejar más o menos un patamar muy perto, 73 millones y 76 millones para 2023. Entonces, ¿qué representa ese consumo de aço en la región? ¿Es bueno? ¿Es alto? Bueno, y ustedes aquí pueden olhar perfectamente, por eso te decía 2 años. Eu não gosto muito das tabelas com muito número, mas gostaria de compartilhar este número sozinho. Na queda de 2020 foi claramente a pior, mas se você olha 2018, 2019, inclusive 2016, 2017, os 4 anos anteriores à pandemia, a média de consumo de aço dá 65 milhões de toneladas. Então, se a gente compara 65 milhões contra 75 de média estes anos, ainda além da queda e além da situação de Latinoamérica, a verdade é que um consumo alto, ainda um patamar alto de consumo de aço, e é uma boa notícia. Mas se você olha em construção, são praticamente a metade. Aqui podemos olhar em porcentagens. Então, isto é um dado importante. Já entrando em construção, basicamente, os últimos anos representou perto de 50% do consumo de todo o aço é a construção. Então, de aqui acho que faz muito sentido discutir durante uma semana como podemos, a pergunta fundamental que falei ao princípio, como podemos entre todos, evidentemente, público, privado, empresas productoras y a cadena de valor toda, cómo podemos incentivar, educar para mayor consumo de aço, considerando que representa hoy, representa 50% de consumo. Obviamente aquí estamos hablando de planos longos y de todas las aplicaciones, construcciones de todo tipo, no solo casas, predios, más también ponches y estradas, etcétera. Por país, interessante. Isto também é interessante. Latinoamérica, eu falei, à esquerda, 50% mais ou menos, mas aqui temos bastante diferenças, não? Colômbia, por exemplo, tem muita mais representatividade da construção. não é tanto porque tenha mais construção per capita, mas sim porque tem menos indústria per capita. Brasil, por exemplo, o caso contrário, tem muita indústria forte, então por isso a construção, quando repartimos o consumo de aço, dá um pouco menor, mas a verdade é que, evidentemente, todos os países têm uma representatividade muito importante. Agora, só uma tabela a mais, e deixo de mostrar tabelas, que eu não gosto. Já mostrei 2, mas não gosto. Você me obrigou a mostrar tabelas. Mas eu gosto deste dado. A gente não alcança com analisar os dados de consumo de aço e produção sem entender o que passa com os setores consumidores de aço. Recién mostrei os 5 ou 6 principais setores de consumidores de aço. Aqui temos os 4 principais. Se vocês olham, esto é primeiro trimestre 2022 versus primer trimestre de 2021. LATAM, vamos a ver o calidad de LATAM. Todos sectores, con la excepción de maquinaria mecánica, que es más pequeña, todos sectores mostrando una queda. Obviamente, las razones, todos sabemos, posiblemente guerra en Europa, inflación global, inflación local, Brasil, Argentina, Colombia, todos con inflación en los países, los gobiernos subiendo las tasas de juros para combatir esa inflación. Entonces, el principal sector afectado por esas políticas monetarias, económicas, obviamente es la construcción. Então, se você olha Brasil pontualmente, quase 10% o primeiro trimestre e o patamar do segundo trimestre vai dar mais ou menos perto daí. Então, conjunturalmente, semáforo um pouco mais vermelho que verde, conjunturalmente para este ano, mas lembrando, 75 milhões de toneladas de consumo de aço, com uma média nos próximos 2 anos, que é gran patamar. Agora, fechando. Só reflexiones, aqui não tem muito dado, 2, 3 ideias que eu gosto de trazer aqui, para depois já dar lugar aos especialistas. Também, a pergunta fundamental, como incentivamos o consumo de aço na construção? E o VP de comercial da Arcelor falou de muitas causas que podem responder a esta pergunta, e ele falou de uma questão cultural, falou de carga tributária, sempre, Brasil, Argentina, eu sou argentino, así que por eso falo muito da Argentina, carga tributária, conocemos muito disso. Falta de educação, falou aqui o doutor também, eu falei também um pouquinho disso, como faltan profissionais mais preparados. Evidentemente, se os meninos na engenharia civil têm a metade de horas de construção em aço que construção em concreto, evidentemente, quando saem da universidade, eles vão querer trabalhar com construção tradicional, evidentemente. Mas eu gosto de ser um pouco mais filosófico aqui para o longo prazo. E acho que todas são causas válidas. Algumas são mais consequências que causas. E acho que, para mim, a questão cultural é mais importante. E se começamos a conectar o consumo de aço com um tema energético, um tema de mudança climática, já começamos a falar de algo cultural também. Evidentemente, o tema de cambio climático é uma questão cultural, además de que es una cuestión real que está aconteciendo, mas o que mudó en los últimos años no es que el planeta está aqueciendo más rápido, más lento. O que mudó es que muchas generaciones, especialmente los más jóvenes, están mudando su forma de pensar en relación al medio ambiente. Entonces, si conectamos ese tema con la construcción en aço, yo creo que tenemos una oportunidad de mudar esa parte cultural que para mí, acho que es la principal causa de no uso de aço. Entonces, por eso aquí hablamos de fuerzas. A transição verde é uma força, além da inovação tecnológica que ajuda a isso, mas principalmente a primeira força, eu acho que vai ser o que vai transformar nos próximos 10, 15, 20 anos muitas coisas. Então, a questão impositiva vai ter que ser resolvida, porque a gente vai querer produzir mais aço para construir mais em aço. As questões burocráticas nos nossos países vão ter que ser resolvidas, as universidades vão ter que se adaptar também. Então, eu acho que a veces estamos intentando puxar solo de embaixo para encima algunas cuestiones como educación y impuestos, mas a veces no vemos unas fuerzas que vienen de encima que van a ayudar, por lo menos, a hacer también a fuerza de encima para embaixo y embaixo para encima. Entonces, eu gosto de hablar de estos dos grandes efeitos. Aquí esto está basado en un informe de McKinsey que habla de básicamente 2 grandes sectores que van a ser muy impactados por las mudanzas climáticas y la tecnología, que son la movilidad en áreas urbanas, las ciudades, y obviamente a construcción en toda energía e infraestructura, obviamente impactando el consumo de aço que estamos hablando hoy. Vou fechando. ¿Por qué las ciudades son tan importantes? Nos preguntamos, evidentemente, también basados en datos de McKinsey y de Banco Mundial, dois, três dadinhos interessantes para ter em conta que vão mudar essas forças também. 80% do PIB global é gerado nas cidades. 2/3 do consumo mundial de energia também consumido pelas ciudades, y eso va a continuar creciendo. De acuerdo al estudio McKinsey, hoy estamos en 57 y 58% de urbanización de las ciudades. Eso va a continuar creciendo 60% para 2030 y perto de 70% para 2050. Entonces, esto es una fuerza, como falo, que no va a parar posiblemente y la gente va a tener que se adaptar para eso. Y acho que una adaptación va a ser precisamente todas las mudanzas que vamos a tener que hacer para construir más en eso. Mas o efeito colateral, eu falaria de essas mudanças, é justamente o que estamos falando, a poluição, o efeito estufa, os efeitos de gases de efeito estufa, que são evidentemente emitidos também pelas cidades maiormente. Então, para ir concluindo, aqui acho que está a oportunidade justamente. Olhem este tabela que eu deixei igual, acho que não é a melhor imagem, mas é muito simples de entender gráficamente, também de McKinsey. ¿Por qué o aço es tan importante cuando unimos estas duas cuestiones? Desenvolvimiento económico de Latinoamérica, en este caso, más sustentablemente. ¿Por qué o aço comienza a ser fundamental para esto y por qué estoy muy optimista con la construcción en aço? Por este cuadrinho, entre otras cosas, más este muy gráfico, na columna, tenemos materiales, básicamente, y na derecha, na horizontal, tenemos todos los tipos de energías que van a ser necesarias para la mudanza climática o que ya son necesarias para la mudanza climática. O aço, primer material que participa prácticamente todas, o no prácticamente todas las energías principales precisan directa o indirectamente do aço. Entonces, por eso falamos que o aço es parte de la solución. Precisamos más aço, precisamos construir más casas, precisamos construir principalmente en Latinoamérica también por un déficit habitacional, mas solo con la mudanza climática o aço va a tener un rol fundamental para los próximos 10, 15, 20 años. Ahora, desde el acero tenemos una agenda activa para intentar colocar nuestro granito de arena en esta discusión. Aquí también se faló hoy de muchas cuestiones que tenemos que hacer. Es un trabajo lento de todos los días. Estos ámbitos como ABM, y de lo cual agradezco a Geraldo a convite, porque acho que son los ámbitos donde tenemos que discutir, concientizar, el uso que intento hacer con esta presentación, 10 minutos, concientizar, tirar algunas reflexiones, mas estas son algunas cuestiones que a gente colocó un position paper que a gente emitió en el acero, junto a World Steel, el año pasado. Aquí traje algunas cuestiones fundamentales de corto y largo plazo para atingir desde el público y lo privado. Entonces, en cuanto a urgencias, para baixar a pegada de efeito estufa do aço, si va a tener que ser tan necesario para construir, vamos también a tener que hacer una famosa descarbonización de nuestra industria, que a gente está haciendo ya mucha cosa, mas eu acho que tenemos tres cosas no curto y medio plazo muy indispensables, que son as fontes renovables, que vamos a hablar mucho de eso, a sucata, para producir mais aço verde, se precisa muita mais sucata, y o gas natural como transición. No medio, antes de hablar de green hydrogen o carbon capture, que también estoy mencionado aquí, antes de eso, hallamos que desde el acero que o gas natural va a ser muy importante por su costo y por su disponibilidad para transicionar esa matriz energética. Mas eu trouxe también el punto 2, sector privado. Eu trabalhei no sector público en Argentina, 4 años, y eu acredito personalmente que siempre desde el sector privado esperamos muchas más soluciones del sector público y tenemos muchas más quejas que soluciones, que propuestas. Y en estos temas tan complejos de largo plazo, yo también acredito que los gobiernos no tienen ni idea de qué hacer, ni idea. Generalmente tienen muy poca noción de qué hacer. Entonces, es un sector privado, específico, técnico, que tiene mucha más información para brindar soluciones y no tanta queja. Entonces, para mí, yo siempre falo, além das cuestiones públicas, también la cuestión del sector privado. Para eso, al acero también cumple un rol, igual que ASO Brasil, en Brasil, de colocar en la mesa estas cuestiones y después colocar esas cuestiones en las mesas de los sectores públicos de gobiernos de turno. Y ahora sí, aquí fecho con estos dadinhos interesantes y con las últimas reflexiones, yo ya falei de la oportunidad que tiene Latinoamérica, que, para ustedes saber, también parte de una situación Hoy, bastante más favorable en cuanto a medición de gases de efecto estufa. Aquí tenemos una medición feita entre el acero, cru y world steel. A gente tiene una media global. Aquí estamos hablando de toneladas de CO2 por cada tonelada producida de azo bruto. 1,89 es la media global. Latinoamérica está bastante en baixo, 1,66. Y China, 2,2. Entonces, casi 2,2. Entonces, cuando hablamos mucho de defensa comercial, ahora ya no hablamos solo de defensa comercial y de empleos latinoamericanos, que por supuesto que continuamos hablando, es muy importante. La industria en Latinoamérica genera 1,3 millones de empleos directos e indirectos solo a industria de azo. Entonces, cuando a gente importa azo de China, no solo está, obviamente, tirando empleos de la región, mas también ahora está trayendo un azo que tiene una 40% más de pegada de CO2 para la atmósfera. Entonces, por eso acho que el mundo va a mudar mucho y estas son las fuerzas que estamos viendo que van a hacer esas mudanzas. Mas si también colocamos un dado duro de consumo per cápita, con esto voy fechando, evidentemente para hacer un desenvolvimiento económico, a gente va a precisar azo. Es por eso que Europa tiene casi 3 veces más de consumo de azo que la media de Latinoamérica. China, para vos saber, no está aquí dado, mas consume 600 kilos per cápita. Mas Latinoamérica tiene una oportunidad y una necesidad, las dos cosas. Mas tenemos que hacer esa mudanza cuidando el medio ambiente. Entonces, por eso, o azo va a ser, evidentemente, o material fundamental para esa transición. Muy obrigado. Obrigado. Bom, agora sim, vou ler os nomes de meus parceiros aqui. Vou apresentar primeiro a Bassam Burgan. Ele é diretor do Steel Construction Institute do United Kingdom. Ele está aqui. Bassam, welcome. In second place, bueno, sorry, in English. Tengo una bagunza en español, inglés y portuñol. Carlos Revelo, disculpa. Él es profesor de la Universidad de Coimbra y también es pesquisador del Institute for Sustainability and Innovation in Structural Engineering. Luis Pupín, ele é engenheiro mecânico com especialização na USP em gestão de projetos estruturais e MBA em gestão de projetos. Bem-vindo. E, aproveitando as mudanças da pandemia, virtualmente temos na tela, vamos ter na tela a nosso quarto palestrante, Luis Simões. Ele é vice-reitor da Universidade de Coimbra também, de Portugal, y también director del Institute for Sustainability and Innovation in Structural Engineering. Bienvenidos a todos. Muy obrigado. Vamos a hablar.
Okay, thank you very much for the introduction. Good morning, ladies and gentlemen. It's a great pleasure for me to be here, and I would like to thank CBMM for their invitation and ABM for all the organization that has gone into this. I will start with a few words about my organization, the Steel Construction Institute, SCI, and the background to how it's come into existence. In the period between the Second World War and the middle of the 1980s, steel was not a very popular construction material in the UK. And in fact, UK government encouraged civil engineers to design in reinforced concrete because they wanted to preserve steel for military applications. So during that period, a whole generation of engineers grew up designing in reinforced concrete and not being able to design in steel. So we were established to try and convert that. Now, engineers work on fixed fees, under time pressures. They don't have time when a new project comes in to explore a lot of new things. They have a tendency to look at what they did last time on the last project and then adapt it for the next project. So we needed, in order to succeed, to break that circle. We were established in 1986 as an independent organization. We were not owned by a steel producer. We were completely independent. And we adopted a strategy that had a number of strands. The first one, given what I said about design engineers, was to try and make design in steel as easy as possible for structural engineers. And in doing that, we produced a lot of guidance. We've published over the years over 400 titles, 400 books, none of them academic, all of them very practical guidance with design examples that help engineers step by step in designing different forms of steel construction. We also wanted to remove certain perceptions, certain barriers. For example, people believed that fire was a problem for steel. Well, of course, it's something you have to design for. It's another design condition, and it's the same for every other material. We adopted the communication programs that included magazines, papers, courses, seminars, etc., to familiarize engineers with the information, as well as a communications program with universities. And there was a need to introduce continuous innovation so that new products, more competitive products, are coming onto the markets all the time. And for that, we worked with product manufacturers to help them with their product development and with the introduction of new products. And the strategy has largely worked. The market share for steel, you can see on this slide, for multi-story buildings, went up from below 50% in the 1980s to it peaked at about 72, 73% around the time of the financial crisis, and it has settled at about 66%. In the case of industrial buildings, the market is now completely dominated by steel construction, with over 98% being in steel. But of course, as we've heard in a number of presentations today, construction is very resource intensive, and it's estimated that around 50% of resources that are taken out of the ground go into construction. Also, as we've heard, global demand for built environment is growing, and it's predicted to double by 2060. And to achieve what was agreed in the famous Paris Agreement in 2015, the steel sector needs to reduce its greenhouse gas emissions by 65% by 2050. So the current increase in demand is not sustainable in the way it has been up until now. Now, we've heard a lot about the supply side and what steel producers are doing to reduce the carbon footprint of steel on the production side. I'm going to focus more on the demand side. I'm going to use three examples. How we achieve greater efficiency with less material, how we not just recycle steel. Steel is already accepted as a material that's 100% recyclable, but how we reuse steel to reduce the carbon footprint further. And then the third example is looking at a new application for steel in clean energy generation, and I'm going to look at an application in the nuclear energy generation sector. So starting with the first of these, the idea here is we can of course design more efficiently, less conservatively, and so use less material. But I'm going to look at using higher performance materials to achieve the objective that we want to achieve for the design with less material. Now, what do we mean by high-strength steel? It means different things in different geographical locations. If we talk about China, for example, S355 is considered to be high-strength steel. In the UK and Europe, S355 is the most common structural grade, and so when we talk about high-strength steel, it's typically S420 and upwards. Now, what can it achieve? Well, in the right application, it can achieve lighter structures. That leads to reduced welding because we're using smaller thicknesses. It leads to lower demand on transportation and handling, all of which consumes less energy. And of course, if the section sizes, especially for columns, become smaller, then you have more habitable space because the structure isn't taking as much space as it otherwise would, and that's particularly important in high-rise buildings. So those three middle bullet points, what they mean is that we would use less material with a smaller carbon footprint, and there are applications for higher strength steels in high-rise buildings, in long-span structures, in bridges. Every application where the design is not governed by either buckling or by deflection is a candidate for using high-strength steel. Just to look at some examples, and this is a comparison between the standard grade for us, S355, and grades 460 and 690. If you look at the first row, we're comparing the saving in carbon and in weight, and you can see that going to S460 is saving 24% in weight, 11% in carbon. In the case of S690, we're saving 38% in weight and 24% in carbon, and so on. If you look at the bottom of the table for columns, for example, for a 10-story building, you're saving 22% weight, 39% in the case of S690, and then for carbon, you're saving 12% and 36%. If you look at cost, the picture is a bit more confused because we're not always comparing like with like. So going back to the top row, when we design those 9-meter beams in S355, there are readily available rolled sections that we can use. However, there aren't suitable sections in S460 or S690, and so we end up designing these as plate girders by welding plates together. And so that tends to cost more. And so you see that even though we're saving in weight and carbon, for that particular example, there is higher cost because we're not comparing rolled sections with rolled sections, we're comparing rolled sections with fabricated sections. The second row is more interesting because here we're comparing like with like. So everything on the second row is made out of fabricated sections because we need deep sections even in S355 which aren't available as rolled sections. And here you can see that there's a saving across the board, including a saving in cost. Now, one of the barriers to designers is if a particular grade is not covered by design codes because they don't know where to turn to. Now, in the case of high-strength steels in Europe, the Euro codes already cover grades up to 460 for design and up to 700 for fabrication. There is a new generation of Euro codes which will be published next, probably over the next 3 years, and these take us up even further. So there is the main part of the Euro code will go up to 700, and there will be an additional part which has been written, and that will cover up to S960. And our job at SCI is to support designers by making design easy, so we have published a design guide that deals with the design and fabrication of high-strength steels, and this is a publication that was sponsored by a number of industrial organizations, which included CBMM, and it's being translated into Chinese and also localized for the Chinese market based on Chinese standards and so on. Moving now on to the next part, which is reusing steel. Now, we have two scenarios here. First of all, the idea is instead of, as often happens with reinforced concrete, you have what's called downcycling, where when a building reaches the end of its life, it's crushed, and some of it might be used in aggregate, some of it might go into landfill. Steel lends itself to being demountable, so you can take the building down as components, and then those components can be reused elsewhere. Now, we have two possible scenarios here. there is already a lot of steel in existing buildings. So how do we go about reusing that steel when those buildings get to the end of their life? And then there is the scenario looking forward. What can we do today in order to make the buildings that we're going to build in the future more reusable? How can we make the steel in those buildings more reusable? So taking the first scenario, what we need essentially is to be able to classify the steel. We need to know what it is we're dealing with when we take a building down. What are the properties of the steel that is in that building? And we can achieve that using testing, sampling, and we also need to know whether we can use the same safety factors, for example, on the second-hand steel as we did on the original steel. And so working with a number of industry partners, both in the UK and in Europe, we have produced the first protocol that deals with reusing steel. This is published and it's downloadable from our website. There's a lot of both practical and academic research that has gone into this. And thankfully, the European standard for fabrication of steel structures already permits the use of reclaimed steel, of second-hand steel, as long as the relevant properties of that steel are known and documented. So knowing those properties is crucial, and what we do in that protocol is we define the responsibilities of the different parties in the supply chain. We define how stockists need to collect that steel and store it, and we define the testing requirements that need to take place in order to establish the properties of the steel so that it can then be documented and resold with the appropriate certificates. Now, looking forward to the future, what we can do to make steel reusable is greater standardization, is to design the steel so that it can be dismantled easily, and to use digital information to help us know what the properties of the steel are. We've looked at two examples. The first is industrial buildings, and the reason is that this is a market for steel that is dominant. As I said earlier, in the UK, 98% of this type of building is framed in steel. And there are things that we can do to the detailing of those buildings that makes them more easily demountable without losing any section of the steel members. So currently, we typically strengthen the joints in these members because of the very long span using what's called haunches. These are these pieces that are attached to the apex and to the joint with the column to make those joints more rigid. Now, instead of welding these to the beams, to the rafters, we can bolt them, and that when we come to dismantle the building, instead of having to cut them and losing a section of the member, because they can be quite long, these, if we bolt them, they can be unbolted, and you have the full length of the member readily available to be reused. Another example in multi-story buildings is composite floors. Now, composite floors is one of the technologies, one of the innovations that in the 80s and going forward has made multi-story buildings very competitive, because it's a very efficient use of materials. You're using steel and concrete together to the best advantage of both materials. It's lightweight, it's very fast to construct, and it's very cost effective. The problem with this form of construction is that we weld these studs through the deck onto the beams to achieve composite construction, so that the steel and the concrete are locked together and act together. And that makes dismantling this type of construction quite difficult, and it makes separating the steel from the concrete quite difficult. So what we have looked at is replacing those welded studs with bolted studs. So instead of this we are now going to using a stud that is bolted to the steel beam rather than welded to it. And then it becomes much more easy to unbolt the studs and separate the slab from the beam. And we've also looked at ways of dividing the slab up into strips so that the slab itself can be reusable, and that makes an even better economic case for reusing composite construction. And again, we have produced a design guide, which is also available to download from the website, which follows Eurocode 4, the European standard for design of composite structures, and that deals with how you design demountable composite floors, and it's based on an extensive series of tests that was done within a European project working with a number of institutes and universities in the UK and Europe. Now, I mentioned the role of digitization as well, and we already largely now work with building information models to help with the coordination of projects. And those building information models for steel store all the details of the members, so the length, the weight, the steel grade, it's all available in the model. So it would not be that difficult to add to that information, attach to that information the mill certificate and the environmental product declaration for those members so that they are available next time we come to reuse the steel. And now moving on to the final part of the presentation, looking at the use of steel in clean energy generation and specifically in the nuclear sector. Now this is really quite a nice opportunity for steel construction because up until now, the nuclear industry has been 100% dominated by reinforced concrete. Steel has not really had a role to play in the buildings on nuclear power plant other than in the reinforcing bars to reinforced concrete. Now, what I'm talking about here is a form of construction for walls that's made out of two steel plates that have these shear studs on them, and then you fill the space between the plates with concrete. And these tend to be used, these are proposed to be used for walls. And then for floors, it's a single skin form of construction, which is made up of a steel plate and these T-stiffeners to give the plate some rigidity. And again, we have the same type of shear studs. So these are used for the floors. The vertical double skin elements are used for the walls. One of the problems that has been in nuclear power projects, and I'm sure everybody knows that always nuclear power projects run over time, over budget, and one of the things that cause this in the civil works is the density of reinforcement in these structures, which causes an awful lot of clashes and an awful lot of problems. The idea with this form of construction is you build those modules in the factory, you bring them to site in the largest size that you can transport, you assemble them on site to the largest size and weight that the crane can lift on site, and then you lift them into position. And the advantage is that there can be a lot of parallel working between site and the factory, and so you are taking risk out of the construction process. This is an example of what these look like in practice. So this is the double skin form. This is the single skin form for floors. The double skin form for walls, as we look at it like this, it's not very practical because you can't, it's very difficult to handle two steel plates that are separate. They are very flexible to lift them, to move them around. So what we do is we join them together. And there's different ways that have been proposed to join them together using either bars that are welded to both plates or bolted to both plates or some form of ribs or trusses. So there's lots of alternatives that have been tried. Now, when you compare these with reinforced concrete, there are a number of obvious advantages. The steel plate acts as reinforcement to the concrete because it's locked into the concrete using these shear studs on the plates, so you no longer require reinforcing bars in the concrete. It's achieved by the steel plates, and because the steel plates are on the outside of the concrete, that gives the maximum lever arm possible, so it makes the structure a lot more efficient. And actually, it is possible to make the walls thinner to achieve the same strength in this form of construction compared with reinforced concrete. With concrete, you need to put up formwork to pour the concrete into, and then you have to strip the formwork, and you may need to do some patching up, some repair work behind the formwork. With this form of construction, the steel plates act as permanent formwork, so they remain in place. You've eliminated two operations, putting up the formwork and then removing it. There are some applications, particularly in the nuclear industry, where you require water tightness, and again, the steel plates provide a watertight membrane. Because of all of these things, it is very fast to construct using this method. And there's one further issue, again, which causes a lot of problems on nuclear power plant, and that is what's called embedded plates. Now, it's best to explain this with some pictures. If you look at all the patchwork on the walls, on the ceiling, all these little squares, this is what's called embedded plates. And these are put in there to support items of electrical and mechanical equipment. Now, on a typical power plant project, there is something like 100,000 of these. And when you have a steel plate that's locked into the concrete with shear studs, you don't need any of this because you can attach directly to the steel plates. The embedded plates, if you haven't seen them, look something like this. So it's a steel plate and it has these studs. So that's exactly like the form of construction that we are using, and it's available on the walls everywhere. This shows you how these embedded plates are being fixed into the concrete, and this is the sort of reinforcement density that you get in nuclear power plant. So getting these studs to fit into the reinforcement without clashing is a major issue. And if you have an aerial view here, you can see how many of these there are, and every one of them has to be fitted by hand. So eliminating this is a major advantage for the nuclear industry. There are other applications for this type of construction, and it has already been used in core walls for multi-story buildings. In Europe, this is the first project on which it was used to build the core wall for the building. Now, in multi-story buildings, the core is always on the critical path. Nothing can go faster than the core can go up. And so if you're building the core in reinforced concrete, that controls the speed at which the rest of the structure can follow. This building was running into trouble with the program, and the program for the core was 8 weeks. This form of construction was then proposed, and the core was built on site in just 40 hours. Now, there's a much more impressive project that was recently completed in the US. It's the Rainier Square in Seattle. It was completed in 2020. This is a 58-story building, and this project, again, came very close to being shelved by the developer because the developer was not happy with the length of time it was going to take to complete the building. Until the designers proposed this form of construction for the core, and this is a comparison between the proposed program using reinforced concrete and what was actually achieved using this double skin core walls. So the construction time for the structure was actually halved. And you have the additional advantage that you're separating the trades. So the steelwork can go up, the core with the beams attached to the core and the columns and then the concrete can follow afterwards. There's also always problems with attaching steel beams to concrete core walls. And again, when you do it like this, you're attaching steel to steel, which is a lot simpler. So for the nuclear industry, we're currently running a project in which EDF, Électricité de France, is one of the major partners. And what we're doing is we're constructing a building out of this type of construction to develop construction expertise and to measure the time and the cost it takes to construct one of these buildings. The building that we've selected for the project is a replica of the EDF diesel generator building. Now, this building was, there's 52 of these buildings that have been built in reinforced concrete by EDF or on their nuclear power sites as a post-Fukushima safety measure. So they provide the power to cool the reactor as a final when everything else fails. We picked it because there's so much data on this building. When you've built 52 of these, you know exactly how long it takes, how much it costs. So it gives us a very good data base to compare with. Now, we know from that data that it takes 9 months to build the structure in reinforced concrete, and the target that we have set ourselves is to complete the structure in half of that time, in 4.5 months. The building has been designed. We made extensive use of building information models to coordinate the work of the designer, the fabricator, and the main contractor. And it was designed using another SCI design guide that we have produced in a previous project. And the modules have been fabricated. You can see them here in the fabrication shop after they've just been painted. And we started last month to construct this building on site at a site which is just southeast of Paris. So first of all, the raft foundation is constructed in the usual way, but what is very important here is to ensure that the starter bars are located very accurately so you don't get any clashes with the shear studs on the plates. And again, this is where using building information models was absolutely crucial, because any clashes, we could detect them in the model before we had any problems on site. All we had to do on site was make sure things go in the right place. And then the modules are craned one by one into position, and you actually are able to build extremely quickly. This is an aerial picture from a camera on the tower crane. So this is the first level of the building completed. The building is in 6 levels. Then the working platform goes on, and another advantage is that the working platform can be attached to the structure, so it doesn't need its own supporting structure. And then you start to build the next level and so on. And this picture I actually downloaded this morning. I can access the camera on the tower crane. And so this is where we're at this morning. And just before I got up, I had another look, and most of the second level is now built. So I hope I've been able to share with you some of the things that are currently occupying us in the UK as a high priority. Thank you very much.